In this section we will study LTE traffic handling. After completing this section, you will be able to summarize the steps involved in handling downlink and uplink data traffic. Describe how channel conditions are reported by the UE. Explain the role of the eNode B scheduler for downlink and uplink data transmission. Describe the HARQ, Hybrid Automatic Repeat Request, procedure for downlink and uplink data handling. To begin our discussion of downlink data transfer in LTE, we must first understand the Channel Quality Indicator, CQI, which is reported to the ENB by the UE. In LTE, the coding and modulation schemes for downlink transmission are not fixed. Instead, they are adapted to the airlink conditions. CQI is a mechanism the UE can use to offer feedback about these conditions to the ENB. So, we can say that CQI is an indicator of downlink conditions as perceived by the UE. It is important to note that the derivation of CQI by the UE is not standardized, but rather proprietary to the manufacturer of the UE, which can also include reference signal measurements and other information like block error rate, BLER. The measured quality of these signals helps the UE to determine the largest block size and modulation rate that it is capable of receiving. Using this information, the UE will encode a CQI index which is reported to the ENB using the Physical Uplink Control Channel, PUCCH, or, if uplink bandwidth has been allocated, it will include it on the Physical Uplink Shared Channel, PUSH. It should be noted that depending upon the operator configuration, CQI reporting may be established as periodic or aperiodic, meaning CQI can be requested by the ENB as needed. EUTRA supports 3 types of CQI reporting, and UE can be configured in either of 3 types. 1. Wideband CQI, used to provide channel quality information for entire system bandwidth of the cell. 2. UE selected subband CQI. In this type UE selects a subband, a subset of RB, to report CQI value. ENB allocates resources out of that subband to UE. 3. Higher layer configured CQI, used only in aperiodic CQI reporting. Network instructs the UE about the subbands. The CQI index is the UE's indication of downlink channel quality, and therefore the rate at which the ENB can schedule downlink data. Good downlink channel conditions indicated by a higher CQI index will use a higher order modulation scheme, a lower effective coding rate, and be able to achieve higher spectral efficiency for downlink transmissions. In the table, the coding rate indicates how many data bits are present out of 1024 bits after encoding, while the efficiency provides the number of data bits per modulation symbol. For example, CQI index 6 means that the UE can receive 600 to 1024 equals 0.5879 data bits per coded bit, which translates to 2 times 0.5879 equals 1.1758 data bits per symbol, since a single QPSK symbol carries 2 bits. We had learned earlier that the PDCCH carries both downlink and uplink allocation information. This information is encoded on the PDCCH using downlink control information, DCI, elements, DCI, which carries those detailed information for the UEs like which resource block carries UE data, and what kind of demodulation scheme UE have to use to decode data, and what are the UL resource allocations, semi-persistent and dynamic, and some other additional information. There are various formats of DCI depending upon whether it is associated with uplink or downlink allocations and according to how the ENB is allocating resources. The resource allocation information includes the number of resource blocks being used, the modulation scheme used, and support for multiple antenna transmissions. Within the DCI is where we will find the CRNTI or other RNTIs like SIRNTI, RARNTI, etc. Information about the downlink channel conditions is provided by the UE via channel quality reports called Channel Quality Indication, CQI. As discussed earlier, CQI reports are based on the measurements of downlink reference signals. The scheduler in the ENB keeps track of reported CQI values for all mobiles which are RRC connected. Based upon the CQI feedback, the ENB scheduler can adapt the modulation scheme and encoding used to send the data. For downlink transmission, the scheduler decides which UEs will receive data, how much data will be sent, and how it will be transmitted. Downlink data scheduling decisions are made 1000 times per second in the ENB, every transmit time interval, TTI, and send on the PDCCH. A UE always monitors PDCCH to find possible allocation. Each UE scans through the contents of PDCCH for downlink control information, DCI, associated to its CRNTI. If there is a match, the corresponding allocation information tells the UE where to look in the PDSCH and how to decode the data. We should mention that the ENB scheduler also has the ability to establish what is called semi-persistent allocation on the PDCCH. In this case, the DCI will indicate what resources are being allocated and some periodicity where the UE will get the same resource. It is called semi-persistent since a new DCI will have to be sent if the conditions, like modulation scheme, change. The radio channel is very unreliable. To protect the input data bits, LTE uses forward error correction or FEC coding. This allows the receiver to perform error detection and error correction. The encoded symbols are modulated based on the scheduler chosen modulation type. LTE supports QPSK, quadrature phase shift keying, 16 QAM, quadrature amplitude modulation, or 64 QAM modulation for downlink data transmission on PDSCH. Higher modulation order like 16 or 64 QAM resulting in a higher spectral efficiency, which means transmitting more bits per hertz of the utilized bandwidth. A higher spectral efficiency allows greater user and cell data throughput. For example, in QPSK modulating scheme 2 bits are carried by one modulated symbol, while in 16 QAM and 64 QAM modulation schemes 4 and 6 bits are carried by one modulated symbol respectively. Next, the modulation symbols are mapped to OFDMA subcarriers based on allocated resource blocks for this transmission. The HARQ, Hybrid Automatic Repeat Request, uses the technique called soft combining, which does not discard the received bad data with error. With the soft combining, data packets that are not properly decoded are not discarded anymore. The received signal is stored in a buffer, and will be combined with next retransmission. Let us understand this with an example. Suppose eNode B has package P1, P2 and P3 for transmission to UE. The ENB sends a package P1. The package P1 arrives at UE, and is OK. If the package P1 is OK, then the UE sends an HARQ. The transmission continues, and UE is sent a package P2. The package P2 arrives, but let's consider now that it arrives with errors. If the package P2 arrives with errors, the UE sends an HARQ. Now, P2 is stored in HARQ buffer at UE. Continuing, the UE send another package P2.1 that also, let's consider, arrives with errors. UE has then in a buffer, bad package P2, and another package P2.1 which is also bad. Does by combining these two packages, P2 plus P2.1, we have the complete information? Yes. So we send an HARQ. But if the combination of these two packages still does not give us the complete information, the process must continue, and another HARQ is sent. And there we have another retransmission. Now the ENB sends a third package P2.2. Let's consider arrives with errors. UE combines these three packages, P2 plus P2.1 plus P2.2 to get the complete information and sends an HARQ. In our example, we see that the package arrived 3 times wrong. And what is the limit of these retransmissions? Up to 4. Which means we can have up to 4 retransmission in each process. This is the maximum number supported by buffer. The HARQ operation utilizes HARQ at the physical layer, so acknowledgement delay is reduced. Using HARQ, LTE increases the spectrum efficiency and data throughput. The fundamental functionality of the Uplink scheduler is similar to that of the Downlink scheduler. The eNode B must evaluate which UEs require uplink resources, and if possible how much data each UE has needs to send. Unlike in the Downlink, this information is not directly available at the eNode B. Instead, it is reported by UEs using one of the following. Scheduling request, SR, which informs the eNode B that the UE has an unspecified amount of data to send. Buffer status report, BSR, which informs the eNode B that the amount of data the UE has to send is within a predefined range. The UE will send ENS to Radian or BSR on the PUCCH. PUCCH resources are assigned to each UE when transitioning from the RRC idle to RRC connected state. If there is no resource available on the PUCCH to initiate the request, then the UE will start a random access process using the PRACH to obtain an uplink grant. After receiving the scheduling request, the ENB makes the scheduling decision based on various criteria and sends an uplink grant on the PDCCH using a DCI. The UECRNTI is encoded in the DCI to indicate who the allocation is for. The resource allocation information includes resource block assignment. Indicates the number of consecutive physical resource blocks allocated to the UE by starting position and length. Modulation encoding scheme, MCS, indicates which MCS should be used for the UL transmission. Hopping parameters, indicates if the UE should use a predefined RB hopping pattern for frequency diversity on its uplink transmission. When the UE receives an uplink grant in the PDCCH, it is assigned one or more resource blocks and a modulation encoding scheme, MCS, to use. This grant applies to a subframe that is 4 milliseconds, ms, after the subframe that carried the grant. The UE will use the grant to transmit data, user traffic or signaling, in its buffers on the push using the allocated RBs with the indicated MCS. If the UE still has data in its buffers, the UE may send a new BSR with its data transmission. The ENB scheduler needs to manage multiple UE requirements while optimizing resource utilization, COS, and capacity to make the scheduling grant decision. The inputs include the scheduling request, buffer status report, data priority indication, COS requirements, power requirements, channel conditions, etc. The Uplink scheduler manages priorities taking into account the priorities of other UEs in the cell, and the output of the scheduler is the UL scheduling grant, including resource assignment, modulation and coding scheme, and whether the scheduling is dynamic or semi-persistent. Let us see how data packets are formed at the UE. The input data bits are given to the forward error correction or FEC block, which performs error detection and error correction. Before transmission, each stream goes through the process of modulation and SCFDMA resource mapping. LTE uplink transmission supports QPSK, 16 QAM or 64 QAM modulation schemes. The modulated signals are then mapped using SCFDMA resources to generate an SCFDMA signal. SCFDMA mapping is different than downlink OFDM mapping. In SCFDMA, modulation symbols are spread by a discrete Fourier transform or DFT function before mapping the modulation symbols to input subcarriers on IFFT. This step is similar to ARQ or NAC transmission on downlink. On the uplink, ARQ or NAC is transmitted by eNode B. The eNode B sends an ARQ to the UE, indicating it has decoded the information correctly, and the HARQ transmission for this packet can be stopped. Otherwise, an ARQ is sent to request an HARQ retransmission. Uplink HARQ is strictly synchronous. For a given packet, the timing between successive HARQ transmissions is fixed. HARQ transmission for a packet is terminated when an ARQ is received from the eNode B, or when the configured number of HARQ transmissions for the packet is exhausted. In summary, the CQIs collected by the ENB give it an indication of the data rate the UE can support given current downlink conditions. The UE reads the PDCCH, looking for DCIs that tell it if it has data on the PDSCH or a grant to send data on the push. Downlink and uplink data is scheduled every subframe, 1 millisecond. Prior to being scheduled, the UE must let the ENB know what data it has to send and the priority of that data. This completes the module. Click next topic from navigation menu.